We're going to start here in section 7.1, which is area applications. So basically in this section, the situation that we're going to be given is that we're going to look at having two curves or maybe multiple curves and finding the area between those two curves. Now, I'm going to draw out the general idea and then we're going to see how that goes. I'm going to use Desmos calculator to do this. So hopefully we can draw this out nicely. So what I've done is I've graphed out just two equations. Here we have y equals 1/2 x plus 2. That's the line created in red. And y equals 1/2 x squared. You can see we have um, bounded, or excuse me, we can see that in certain regions the line is above, and in certain regions the parabola is above. So we need to specify where at, from what x value to what other x value we're looking at. So for me, I'm just going to take between the x values of 1 and 2. All right. So we have those lines here seen in green. So what we're doing is we're focusing in on this area here. All right, so that area right there. And if I want to find the area between these two curves and between 1 and 2, looking at this area, what I should remember from Calculus 1 is that the area under a curve, when I say under a curve, I mean from the curve down to the x-axis, is given to me by integration. So if I look at the area under the line, it's going to be the total area from the line down to the x-axis. And if I look at the area under this parabola, it's the area from the parabola down to the x-axis. So if you think about that, okay, so basically what I've done here is I've put that graph into paint so I can shade some things. So here's what I'm going to look at. We have three areas. The area under this line down to the x-axis. We know we can get that by integration. We have the area under the line, under the parabola, down to the x-axis. We know we can get that through integration. And we need to create the area from the line down to the parabola in this section. So what we're trying to do is we're trying to find the area in here. Ooh, that's a good, there we go. Trying to find that blue area here. I know how to find the area under the line all the way down to the x-axis. I know also how to find the area in here underneath the parabola. And if you think about the area under the line down to the x-axis is a combination of blue and red. The area under the parabola is the red. So if you take those two areas and subtract them, you're going to end up with just the blue. And so that's the main idea. The main idea is that we can get this integration, we can find the area between two curves by simply integrating and subtracting the two curves. So integrating the difference of the two curves, saying it that way. Now, in this case, when we looked at the line parabola, the line was on top. And so you'd always want to put the one curve that's on top as your f of x and the curve that's on bottom as your g of x. Obviously, that depends on the region because certain points, the region we looked at, the line was on top, but there are other regions where the parabola would be on top. So the f and the g are going to depend upon which one's on top in the region we're looking for. So let's do an example. Let's try to find the area between y equals x plus 4 and y equals x squared minus 2 from x equals -1 to x equals 3. Now, the first thing that I'm going to do in order to complete this problem is I'm going to look at the graphs of these and decide which one's on top in the region that I'm interested in. So let's take a look at that. So there we have things graphed. Now, um, again, I've graphed this on Desmos. You can do this on your calculator as well. You look at -1 to 3. So -1 to 3 was my region. 3 is basically right where these things hit. Again, that's an x value of 3. At the x value of 3, these two curves intersect, so we're looking at that. At -1, that's right here, x value of -1, we're there. So in this region that we're looking at, I guess I could graph this if you'd like. X equals -1, x equals 3. So between these two vertical lines, we can see that the y equals x plus 4 is the piece that's on top. All right, so y equals x plus 4 is the thing that's on top. So what we do is we go and we integrate the things we're going to do. We're going to do the x minus 4, x plus 4, y equals x plus 4 on top, minus x squared minus 2, that's the point on bottom. We're going to integrate that with respect to x, and we're going to integrate that from -1 all the way to 3. Okay? X plus y equals x plus 4 minus y equals x squared minus 2 from -1 to 3. Again, I don't put the y equals part in there because of the way integration is done. Hopefully you remember that from your Calculus 1, how integration works. So that's it. Now, in terms of answering the question, basically we've done all the work that we need to. However, we need to remember how to do an integration. We could do this by hand, or what we're going to do in this class, especially in chapter 7, is we're going to integrate utilizing our calculators. So we're going to pull out our calculators and we're just going to type it in to our calculator, integrating from -1 to 3, x plus 4 minus x squared minus 2. I do have to be a little bit careful about the parentheses and getting those right. All right, so we're just checking again. Y equals x plus 4, y equals x squared minus 2, and we integrate that using our calculator. Instead of me showing you how to do that, usually I would do a show on the overhead, but because I don't have my overhead with me right now, I'm just going to tell you the sequence of keystrokes in the TI-84 in order to get to the integration. There's a math button on the calculator. It is about 4 keys down on the left-hand side of the TI-84. All you have to do is hit math and then go down to option number 9. It should say FNINT. All right, so math 9 FNINT, and that brings up on my calculator, because I have math print on it, that brings up something that looks like this. It looks like an integrate and then some blank stuff and then the D and then a blank. And so all you do is put in the -1 where it needs to go, the 3 where it needs to go, the x plus 4, and then minus. And the key component here is that we put that x squared minus 2 in parentheses. Otherwise, it's not going to think, it won't distribute the minus. So make sure you do go ahead and do that. But when it's all said and done and you press enter, Oh, don't forget the very x at the end. The calculator shoots out a value of 18 point lots and lots and lots of sixes. If you want to call that 18 and 2/3, that's fine as well. Okay, so that's the idea. I forget how many sixes and then a 7 at the end there. So 18 and 2/3. Lots of times when you type things into Moodle, they'll want an exact answer. So they'll want the 18 and 2/3, or they'll want the improper fraction of that. If you don't know how to do the fraction, um, again, if you just hit math, number 1 will change things into a fraction for you. Okay, so you'll either get an improper fraction or a mixed fraction depending on the settings of your calculator. So math number 1 changes things into fractions from decimals if you need that. All right, so mine changes it to 56/3. Okay, so that's the improper. The mixed number is 18 and 2/3. So that's basically the whole thing. In order to find the area between two curves, we subtract those curves and integrate. So what I'd like you to do now is pause this video and try example 2. In a normal class setting, what would happen is I'd go around and look at people and see what they're doing. Obviously, in this situation, it's going to be hard to do that. So pause the video, try to do example 2, and then I will do it as well. Okay, hopefully you did that. So what I've done is I've graphed these. 1/2 y equals 1/2 x to the third plus 2, y equals x plus 1. So I've graphed that. I did that in Desmos. And there you see that. 1/2 x to the third plus 2 is this red curve. Y equals x plus 1 is this blue curve. Now we're looking at between 0 and 2. Again, x values of 0 and 2. And in that region, the red curve is above the blue one. And so what we're looking at, red curve is on top, blue curve is on bottom. So we're going to go red minus blue. Or when we type it into our integration, 1/2 x to the third plus 2 minus the quantity x plus 1. So that's what it looks like. Obviously, we're integrating from 0 to 2 because that's what the bounds are. And I'm just going to type that into my calculator. Once again, math 9 is what we're looking for. I'm currently typing that in. I forgot to type that in earlier. Should have done that. But remember to keep parentheses, and then at the very end, make sure you have that dx in there. All right. So when I press enter, I end up with the number 2. So the area between these two curves is 2. Now, obviously, we haven't been given any units of measurement. So when I say 2, it's 2 square units of some kind, right? I'm not going to require you to label that because who knows what types of units we're using here. But whatever those units are, it's 2 square units, which is kind of an interesting concept because this is a weird kind of a shape. Again, we're talking about from x equals 0 to x equals 2. So from x equals 0 to x equals 2 in this region. Let's zoom in there. So this weird odd shape region has an area which is exactly 2, this whole number. Again, that's a kind of an interesting concept. All right. Well, what if curves intersect? our next idea is what happens when curves intersect. In other words, instead of me giving you from x equals 2 to x equals 0, I'm going to ask, well, how do we find the area between two curves or between a bounded region? So what we mean by bounded region is a region which has a finite area and whose perimeter is defined by curves. Now, sometimes those curves can be two curves like we have here. Sometimes those curves can be three curves. Sometimes we can have four curves, but bounded region such that the perimeter is defined by the curves I'm given. So we can see an F and a G here. We have an F, which is this parabola. We have a G, which is this line. Let's graph both of those and see what they look like. There I've graphed them. Now you can see if you scroll out that there's a lot of different areas around, but the only one that has finite area is this bounded region where my cursor is, right in here. Okay, I'm not going to shade that in because quite frankly, I don't know how. So, but you can see that that is the bounded region where the curves make up the perimeter of that region. Now, if you notice what's happening with these x values, this bounded region starts when we have an x value of 0, all right? And it stops here, where we have an x value of 3. In other words, it starts and stops at intersection points where the two curves intersect. If those intersection points are hard to see, you can always use the trace feature on your calculator to figure those intersection points out. But it's pretty easy to see visually right here that the point 0, 1 and the point 3, 4 are our intersection points for this bounded region. So when we integrate, we're going to integrate from 0 to 3 because that's the start and stop x value of my region, of my bounded region there. Now, the other thing we have to do, as always, is say which curve's on top. In this case, it's the parabola. So that's all we have to do. From there, it's pretty self-explanatory. I know the parabola is on top, so I'm going to put that first. Then I'm going to subtract the line because that's on bottom in my bounded region. And then, just like I said, we're going to integrate this from 0 to 3. I haven't typed it in my calculator yet, so let me do that. When you type that into your calculator, I end up, again, using math number 9 there, I end up with 4.5, or if you want to write that as 9 halves, or 4.5, or anything like that, go right ahead. Again, watch out on WebAssign or Moodle when you type these things in. If it asks you to type them in as a improper fraction, make sure you write it that way. If it says it's okay to use decimals, then it's okay to use decimals. All right, so that's the idea there. So what I'd like you to do, once again, is to pause the video right here and try to do example 4 on your own. Okay, so let's take a look at the graph first. So we're going to find the bounds and figure out which one's on top utilizing the graph. Okay, so I go to Desmos. I've obviously already typed these in. You can see that the bounded region that we're looking at, there's only one bounded region. It's this little one in here. I'm going to zoom into that a little bit. You can see that the square root, or I should say the curve with the square root in it, is the one that's going to be on top in that region. The line is going to be on bottom. And you can also visually see that they intersect when x is 0 and when x is 4. So we're going to be integrating from 0 to 4, the square root of x plus 3 minus 1/2 x plus 3, or 0.5 x plus 3, however we'd like to write that. So there's my integration. Integrating from 0 to 4, the square root of x plus 3 minus 0.5 x plus 3. When it's all said and done, when I put this in my calculator actually gives me out a kind of a weird answer. My calculator gives me out 1.333333 and then 544. So it looks like it's going to be 1 1/3 up until those very last decimals. Now, this is an issue with your calculator that can happen. If you actually did this by hand, you would in fact get 1 1/3, okay? You would have gotten 1 1/3 if you did this by hand. But because of the way the calculator works, it does integration using numerical methods. So as it gets closer and closer and closer, when you have something like a square root and we're integrating close to 0, it's going to have issues right here. And so what happens is that those approximations get better and better and better. And the calculator eventually says, well, the approximation's good enough for me. And so if we actually are dealing with our calculators, basically I need to know that it does that sometimes and be smart enough to realize that point a bunch of threes and then 544 is actually should have been 1/3. Okay? So that's basically how I deal with those types of problems. Now, I would like you to try example 5 on your own. In this case, we have 3 curves that we're dealing with. All right, so here it is. 4 over 2 minus, excuse me, I should say y equals, or g of x equals 4 over 2 minus x, y equals 4, and x equals 0. So let's graph those. 4 over 2 minus x I have here in red. Notice that we have an asymptote right there. Y equals 4 is this horizontal line. X equals 0 is this vertical line. X equals 0 is also known as the y-axis. So when you look at the bounded region, and it has to be, remember, a bounded region where the perimeter is defined by the lines in question. We're looking at this region in here, okay? This region in here, notice the left-hand side is the x equals 0. The very top of this is y equals 4. And the bottom of this is the 4 over 2 minus x. Now, notice that as far as x values go, this region starts at an x value, of 0 and ends at an x value of 1. So when we're going to be integrating, we're going to be integrating from 0 over to 1. The top of this region is going to be my line y equals 4. The bottom of the region is going to be the 4 over 2 minus x. So let's go ahead and type that out. So we're going to integrate from 0 to 1. Y equals 4 is the top region. By the way, hopefully you've noticed that every time we integrate, when we were integrating y equals 4, we're integrating just the equal to parts. We have it solved for y already. And then equals 4 over 2 minus x. There you go. And when we type that into our calculator, I end up with an ugly decimal, 1.227411,278. Okay. Now in this case, that's not a nice fraction. And if we just change the end um, couple of units there, it's not going to actually change into something that's a nice fraction. And this is because when you integrate something like 4 over 2 minus x, we get some ugly things. So we don't have a nice fraction there, nothing that has a good denominator to use. But there it is. Okay. Now, what's going to happen in Moodle or on WebAssign most of the time is it's going to say, well, let's just round this to 2 decimal places or something like that. So you can say equal to, or better yet, you could say approximately equal to 1.23. Okay, so that's the idea. Now, what if we have an arbitrary thing? What if we ask a bad question? For instance, like this one. This one says find the area between f of x equals quantity x minus 1 to the third power and g of x equals x minus 1. So let's graph those. There they are on the graph, and you'll notice something funny. We have actually two different bounded regions. And this is why this question is bad. If I said, find the area of the bounded region between these two curves, well, we have two bounded regions to talk about. So it's a little bit arbitrary what that means. In certain circumstances, that may mean just the area of one of these individual bounded regions. Like for instance, from x equals 0 to x equals 1. In that bounded region, we'd take the cubic polynomial minus the linear polynomial and see what's going on. Or the other bounded region from 1 to 2, you take the linear minus the cubic and see the area there. Now, the other thing it could be referring to is to actually say, let's take these two regions separately and find the area of this guy, find the area of this guy, and add them both up. So it could be the sum of the two bounded regions. That's another question that could be asked. Yet another question that could be asked is to say, well, let's count this region as a positive area and count this other region as a negative area, or vice versa. So if I counted this region as a positive and this region as a negative area, then they would cancel each other out. By the way, there's good reasons to do that, especially if we're talking about something like a profit of a company. At certain points, the revenue might be under the cost, and certain parts, the revenue might be on top of the cost. So sometimes you'd have a positive profit, and sometimes you'd be losing money, so you have negative profit. And so if I just ask you for the area of the bounded region, and there are multiple areas, then it's a bad question. I would need to specify more accurately what's going on. All right? So that's what we mean. If we do have multiple intersections, You can interpret it in lots of different ways. You have to be careful. You could, again, count one area as negative, one as positive. We count everything as positive, or we might just do one of the specific regions. Okay, I'm not going to do those problems because it's not worth the time, but you can see how this can be a little bit trickier. All right, so not every time that a question is asked is it a good question. All right, so this ends our look at section 7.1, and we'll do 7.2 on the next videos.